Hi everyone, my name is Daniel Godet. I'm actually an API Academy member. Today we're going to be covering improving API resiliency using API gateways. And sorry, there was a bit of technical difficulty, so we're starting this session again. So what's the topic? What we're going to start about in terms of agenda? We're going to say and review what is resiliency. Why do we need to have resiliency? And then, since we're talking about API gateways, it's good to have a good understanding what API gateways are. I'm going to do a short overview, as well as provide an example architecture. Then I'm going to jump into the meat of this session, which is going to be API gateway patterns that help improve stability, or in essence, resiliency. And then we'll have a summary of what we covered. So where do we get a definition for resiliency? Well, let's take from a dictionary. Merriam-Webster has a definition, of which they say, resiliency is an ability to recover from or adjust easily to adversity or change. Now, the word adversity might need a little bit more definition, and easily, Merriam-Webster comes to the rescue. We also have the definition of adversity, which is a state or instance of serious or continued difficulty or misfortune. So when we put the two together, we have a definition of resiliency that's an ability to recover from or adjust easily to a state or instance of serious or continued difficulty or misfortune. Now, when you talk about API communication, it's the ability to recover and adjust to really misfortune or difficult situations where, in terms of its access, it's still available, it's still working, still doing what it's supposed to do. But turning it to the other direction in terms of clients, so API developers, API consumers, what does it mean for them when you're resilient? Well, in their perspective, it's all about stability. It's always available. So unbeknownst to them, there's been any problems. So resilient system provides stability. Insofar as when you consume these APIs, they are going to be available. They are resilient. So why do we need resiliency, right? Why is that important? Well, from a technical perspective, I'm going to leverage some quotes from Michael Nygaard in his book, Release It, which I use every day when I talk to my customers in terms of API resiliency, API stability. So he talks about the fact that, and we can all agree with this, things happen in production. Bad things you can't always predict. On top of that, bugs will happen. They can't be eliminated, so they must be survived instead. So that's why we want to look at resiliency from a technical perspective. Now, on the business side, what does it mean, right? Lack of resiliency means downtime. And what's the cost of that downtime? Well, productivity losses. Imagine you don't have access to services, to systems, your employees are stuck, they can't do any work. You're losing productivity, right? So at the heart of these systems are APIs. And if those APIs are not available or are in a state of air condition, you're going to have productivity losses. But if these APIs also help do business transactions to move the business forward, you might actually have lost sales opportunity in terms of a website selling widgets or something. Or if it's your core business that you're actually generating revenue with your APIs, those are possibly missed opportunities. Now, on top of that, though, let's say that someone's using your mobile app, or there's some kind of API that's being leveraged by consumers out there. It can also damage the brand. Maybe it might make your brand seem like it's just not reliable, right? Because the business runs on APIs these days. So when you have lack of resiliency, downtime, your brand is damaged. Now, on top of that, you might actually be providing API services to other external organizations, and those would have service level agreements. So if you have some kind of downtime or where those APIs are not available, not performing up to spec, you could also have additional financial penalties as it comes to service level agreements. And then lastly, you could also have data loss. Right? So when these APIs can't communicate, let's say that systems come down when you're doing this API communication, you could actually lose data. There could be something that in transit that just doesn't get captured again. So those are all risks. There's definitely more, but these are the top 5 that we tend to talk about with a lot of the people that I consult with. So taking that into hand and then looking at how to make APIs more resilient, we're looking at API gateways. So what are API gateways? Well, first and foremost, they're a form of proxy. Right? But specifically, they're a layer 7 proxy. What does that mean? Well, they work at the application layer. So, mostly in today's conversation today is going to be mostly about synchronous APIs. I will talk a little bit about asynchronous towards the end. But when we're talking about API gateways, it's mostly about synchronous HTTP or HTTPS type of traffic. And these layer 7 proxies, API gateways, act as an API front end forwarding requests going to backend services, mostly APIs and web services, but it could be other protocols like a queue, it could be a database, could be to some other systems. It also helps enforce policies. So security policies, governance policies, making sure that what comes in follows regulatory requirements, maybe security policy in your organization. It goes through a whole set of rigorous checks and bounds. And on top of that, when you start looking at orchestration, it can start making multiple calls to different systems. And when you put the two together, for example, having the API gateway talk to some rules engine or other validation systems or an LDAP or database to actually make sure that what happens is correct, it becomes an enforcement point on top of that. So it's very flexible. It's usually more advanced than your average proxy. Now, you keep in mind that a lot of web proxies can also be considered at a very fundamental level an API gateway. But the ones that I'll be focused on today, though, can do a bit more. They can do enforcement policies and orchestration. It can also do protocol bridging. So they don't just talk about HTTP and HTTPS. They can talk JMS. They can talk FTP, SSH, different types of queuing systems other than JMS. So they actually bridge different protocols. Or they can do HTTP2 to HTTP 1.x or vice versa. So they really help bridge that. But they can also bridge things like security contexts. Maybe you've got OAuth 2 in the front, SAML in the back, or basic auth. They also do that kind of bridging as well. But most importantly into this, for API gateways, is that it has full visibility into the requests and responses, which is critical when you're doing some kind of resiliency. You need to know what's going on. You need to have a bit of intelligence in terms of what's going on there. And that's where sometimes some of these other proxies might not necessarily fit the bill to what I'm talking about today, right? So having that full visibility into the payload, the HTTP headers, and additional meta information, requesting IP addresses, where it's going. So it's got full visibility. In essence, actually, API gateways have N+1 visibility because it sees who's coming in, it sees where it's going, as well as the responses. So it can actually give you a good heartbeat to what's going on. And it's also not a bad place to do some tracing as well. But that's not necessarily coverage we're going to do today here as it relates to API gateways and resiliency. Here's an example deployment where we can see where API gateways go, right? So usually, and in cloud environments, there might not necessarily be a DMZ per se, and it's just everything's a trusted zone. But conceptually, what's important here is that you can see there's different API gateways here, and they can connect internal systems and external systems. And every communication goes through an API gateway, right? And what's interesting here, you're seeing all these lines on the left and on the right. And actually what we call that is a butterfly pattern, right? So why is that important? Well, Michael Nygaard in his book, Release It, he talks about the fact that connections actually, this integration is an anti-pattern to resiliency. Ideally, if you had no connections, you'd have a real resilient system, except probably of no use to you because it wouldn't be on any networks. So there has to be a balancing act here. So when you start to connect different things, this butterfly pattern is actually pretty good because it limits the number of connections. Usually you start to 2n number of connections because you have something coming in, something going out. So you have 2 connections, and then it can be more. When you start to do orchestration, you might have a few more API calls, but it's not exponential. Right? That's something that's important here. Now, I will say that when you have this kind of architecture, it does mean that you have a system with a lot of responsibility because you're literally putting all the traffic through this. But nothing stops you from having separate environments. We'll talk about it a little bit later. But what's key here is communication going through these API gateways. Now, what's the opposite of that? Well, then you have something called a Spiderweb pattern. So when everything talks to everything. Nothing wrong with that conceptually in terms of if I've got all this flexibility, all these systems can talk to each other, as a developer, I don't need to worry because now everything just seems to work. Except there's a problem here, right? This can have up to 2 to the power of n connections, right? So now you have exponential growth of number of connections. Now, this is extreme. We don't tend to see this. Usually when you do deployments, it's something in between these two. But it's a lot more difficult to provide resiliency when you have all these connections. Now, you could have something in between where it leans more towards the 2 times n, right? Where you actually don't have as many connections, but sometimes you do have some systems talking to each other. But keep in mind that the more connections you've got, the less easily it'll be to provide resiliency or stability, in other words. So what are we going to talk about today? How do we increase resiliency? Do we just do the butterfly pattern? That seems to solve all our problems. but not really. It's just one of many things, right? So yes, you want to have as few connections as possible, but sometimes within your business processes, you do need to have systems that talk to other systems. That's the benefit you get through this environment, right? So what do we do then? We actually apply stability patterns. So we have a happy medium. So we try to be as much towards that butterfly pattern, right? Not the spider pattern, but then within what we do is we start to apply some of these stability patterns. And actually all these are discussed also in the same book I mentioned earlier by Michael Nygaard, the Release It book. And I've taken a few of these. I've taken 6 of these to talk about today. So with that, there's going to be the timeout, circuit breaker, bulkhead, fail fast, handshaking, and decoupled middleware. And I'll be covering all of these today in today's session. So first things first, the timeout pattern, right? What does that mean? Well, imagine you've got a system that you're talking to back an API, and in this case, we do have an API gateway, but there could not be one as well. And by default, a lot of systems, internal systems, will have a timeout of 60 seconds. So let's say this API, for whatever reason, we don't know why, cannot respond. We're going to put a request in and wait 60 seconds. Now, some browsers or some APIs will wait 30 seconds or maybe 2 minutes, but in this case, let's assume that it's 60 seconds. So for 60 seconds, the system's not doing anything. It's just waiting and waiting and waiting. Now, if it was only one call, well, end user experience is not great, but it's not a big deal. Let's imagine, though, that there's 300 of these going on every second. So we're talking 300 requests a second. And let's say that each one of them is going to take 60 seconds to time out. After 60 seconds, we're going to have 18,000 concurrent connections all of a sudden. Can this API even withstand that many API calls? Maybe, maybe not. You could say, well, we have a cloud-native environment that can just scale out. You know, here's my credit card, just keep scaling out the environment. That usually doesn't work, right? There's a cost to that. So what we're talking about here is actually reducing the default timeouts to something more manageable, to 5 seconds. And now some people might say, 60 seconds, 5 seconds. I've got customers that I've worked with that actually have 300 seconds for timeouts, right? And that problem just exacerbates. Like, it just gets bigger and bigger and bigger. You really have to be careful when you have these long timeout values. It really doesn't work well in environments. Oh, there's a question?
So, do you mind if I...
No, I don't mind. Just gonna...
Oh, yes. Thank you.
Give you the microphone, because we're also live streaming.
Oh, okay. So my question was that what if we put a load balancer between API gateway and the no response condition thing? So that way we can just figure out that the API thing wouldn't get 18,000 requests in a second, right? The load balancer thing will divide the request. So,
and that's a valid question. And usually there is a load balancer in the front and in the back. But imagine behind here there's a single database cluster. It's still going to get 18,000 requests and maybe even more. But you're right. In terms of layer 3, we can start to help minimize that problem. But you're still dealing with 18,000 connections. I actually have a case where I worked with a customer where they had 3,000 agents logged in at the same time. And unbeknownst to this particular customer, their single-page app did 26 concurrent calls. And you can say, well, browsers aren't allowed to do that. Well, the API gateway had at least 30 different names. So it was the same API gateway, but with 30 different names for different APIs. So every time someone would make a call, it would actually generate 26 concurrent calls at the same time with a 60-second timeout value. And the backend environment was getting all these calls. Now, there could actually be up to 9,000 agents at the same time, but just let's go with the 3,000. Imagine having 3,000 requests coming in with, 3,000 clients logging in and using something with a timeout of 60 seconds and is making 26 API calls at the same time concurrently. That's 78,000 calls. Now, this particular customer, their load balancer could only handle 50,000 calls. What do you think happened? Everything just went down. Because now the load balancer, and when it went down, every other communication went down too. Like, it wasn't just this system, it's everything else that the load balancer had. So absolutely, like, taking a defense in depth approach, load balancer can help. But then there's more to it than that, right? So you had developers in this particular case that were told, make the app as responsive as possible. So they had the smart idea of saying, let's do 26 concurrent calls because it's the most responsive. And internally, that's what they did. The actual business owner thought there were 3 business transactions, and that's what they designed the system for, not 26 API calls, right? Behind the scenes. Lesson learned, right? But the thing is, when you're starting to build this, you want to have a system where you can't just say, because that's what they assumed, the load balancer, that's exactly what they assumed, was a load balancer can take care of everything. And in this particular case, they could only do 50,000 concurrent connections. Now, some load balancer can do more, but just keep in mind that this is only for over 60 seconds. What happens in the back end? Well, the front end users kept clicking reload, 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 and reload. So it was always 78,000 plus connections all the time, right? And sometimes they open up an incognito browser and then double the load from that one workstation, even making it worse, right? So the secret here, though, or the answer ends up being have very low timeout values. You know, imagine bringing it down to 500, right? To 5 seconds, sorry, not 500. So we bring it down to 5 seconds, you have a very different scenario, right? So in this case where we had 3,000 clients, that means 15,000 connections, and then they time out.
But then, can we put a rate limit thing out there?
So you're asking if we can add a rate limit, and those are some of the other patterns. So we're going to talk about some of the other patterns in terms of, but in this case here, let's say that, again, we don't know why this is not responding. We don't care. So one thing we want to be careful is we don't want to tightly integrate this to that. The API gateway needs to know what it's doing. Now, there's going to be another pattern we'll talk about called handshaking, where we do health checks. And that's going to help with that. And this way we can implement things like rate limits as well. And absolutely, rate limits can help. And you can put those in place. And they do help in terms of request responses. But businesses want to be careful. If, in this one case for this customer I talked about, this is their #1 system generating revenue generation system. They didn't want to put any rate limits, right? They didn't want to have less sales. They thought load balancer and everything will take care of everything by itself. We actually changed it to 5 seconds and everything resolved the problem, just to put it in perspective. So in the end, changing it to 5 seconds solved the problem temporarily. Then they went back and redesigned the app so we wouldn't do 26 concurrent calls, right? Actually, similar situation, there's actually another company that has a Visio, I'm not going to mention any names, a Visio competitor for online, you know, doing some diagrams. They went from HTTP 1 to HTTP 2 on some of their systems because in the end there was only one concurrent connection. What happened after that? Well, they said their load and system slowed down because the same thing I just told you about this other example happened with HTTP 2. It became very, very, very spiky, and the spikes were way higher because it was HTTP 1. A browser only does up to 6 concurrent connections usually. This was doing 100 concurrent connections, and then the system could not handle that. So again, timeouts are critical to help provide some stability. And the short of it is stop waiting. Just after 5 seconds, you just cut. Don't worry about it. But it's like a dumb, like just let's not think about it. That's the first pattern. The second pattern is circuit breaker. So let's say we have something similar to what I talked about before, and we have an API that works, everything's going good, and that's called a happy path, right? So it's a closed circuit breaker, like a power supply or a circuit breaker for your house, your home, or a fuse. So when everything's working fine, there's no problems, but when you open the circuit breaker, you have some kind of error condition. And instead of talking to this API, you either talk to a cache or a static response. You still provide some kind of response though, right? It's not a timeout. There could still be an error, like a 529, for example, but there's at least something here. The gateway still responds. The front-end client gets some response, okay? That's in terms of an open circuit breaker. Now, it works well, actually, with a timeout pattern. So if this thing gives out, then we can always at least provide something. And the lower the timeout value, the better this is. You know, if you were to say it's a half-second timeout, then end-user experience will be a lot better than waiting 5 seconds, right? So keep that in mind. And in terms of how do we turn it on again? Well, then we have a half-open circuit breaker. So we do a little bit, either one or a few calls to see, is it still available, right? Or we can do the handshake pattern we're going to talk about shortly, right? But is it working or not? And if it is, then we go back to having the closed circuit and you're back on track. I know I'm running a little bit low on time here, so I'm going to have to go a little bit faster. So the next pattern is the bulkhead pattern. And in terms of bulkhead, think about a ship or a boat, right? where we have different bulkheads that if you ever have some kind of collision or something where water comes in, you minimize the impact. You contain the damage or the impact. So this is an example of a ship where you can see all of these bulkheads. So if there's any kind of damage, water only goes in one place and the boat doesn't sink, or at least gives you enough time to deal with the problem, right? So when we're talking about that with API gateways, there's many, many ways to look at bulkhead patterns. So bulkhead patterns could be, I want to have 2 separate racks of servers, separate VMs. When we're talking about API gateways, we're talking about having different channels, either for different listener pools, right? Maybe I've got a fast lane, slow lane, because remember before we were talking about API calls, and have something that takes 60 seconds to respond is not good for performance, and it eats up a lot of resources. So I actually have customers that I work with where they have what's called a slow lane and fast lane. Dedicated resources, dedicated path for slow lanes, which because then you start to accumulate a lot of calls, but you limit that pool to a small number, so you can't have too many of those going on at the same time. And then the rest of your traffic goes through there, where that would be the fast lane. The gateway, because it's got full visibility in terms of those payloads, it can make a decision. Do I go here or do I go there? Or it could be based on endpoints, it could be based on method calls, and it could even be made, I'm doing a bank transaction, and if it's a $1,000 transaction, you go here. If it's a $3,000 transaction or more, you go there. So you can do that with the bulkhead pattern. You can also do it for business critical processes. But in essence, you're doing dynamic routing and you're limiting the impact. So if this, in the backend, let's say the backend here crashes. So let's say you're doing a place where you're doing queries where you get lists and you can actually do some transactions. Well, maybe, nice to have is, I want to get additional details on items. Well, maybe that one gets dropped and you just do the business critical functions on the other one. So that's the bulkhead pattern. The gateway is very well placed to do that. It doesn't necessarily hit the backend APIs if it doesn't need to. Remember, when we're talking about this, we also talk about failure, right? So let's say earlier we're talking about timeout patterns. That means we actually made a call to see if something worked. Well, what if we already know it's down? Well, that's called the fail fast pattern. We don't even process the request, or at least it never makes it to the back end or to the front end. So let's say that from a front end perspective, well, actually, let's go here. So let's say from a back end, this is got some kind of error condition, maybe the timeout, maybe some other reasons. Well, if the gateway already knows this, the request comes in, we're just going to fail it. Because why even bother doing the 5-second timeout if we know it's not going to work? But it also works well if you have the circuit breaker pattern as well. And on top of that, what about front-end clients, right? I'm going to put an invalid API or invalid characters. Well, never make, some systems will actually make the backend call and do all that stuff. Even though it's an invalid request, comes to the gateway with an error, and then we error out. Why bother making this call? Even though the service was right, this had an invalid input, right? Either non-compliant requests, maybe characters, maybe someone's trying to hack me. Who knows, right? Maybe it wasn't authenticated, authorized correctly. Maybe this person or this particular request wasn't allowed to do this. Don't bother making other requests. Now you can say, well, that seems like it makes a lot of sense. The reality is a lot of systems will make the call anyways first and then error it out. Fail fast. Don't bother with it, right? So in the end, decide to stop processing the request. So with that, I was talking about this a few times, this handshaking pattern. So this is where we can do things like throttling. We were talking about API calls and API rate limits. This is where we do handshaking in terms of the gateway can implement some kind of throttling. And this can be on many, many different levels, right? In this case here, I've got an example where we're doing health check probes. Are these systems available? Yes, no. And maybe since I'm also aware of all calls going back in and out, I can have an assessment that things are getting kind of tight. I need to limit and maybe do dynamic throttling, for example. Maybe these, and let's say that the health check probe fails. Then you look at things like the other patterns I talked about before, like a circuit breaker or fail fast, right? So you start to look at having and multiplying these different patterns. And by the way, I want to make sure it's not the goal to have as many of these patterns on, right? It's not, oh, I've got 10 of these or 6 of those. That's not the premise here. You use what you need for your particular environment in your particular cases. But you can see how they can work well together, right? In this case here, we're going to look at keep alive. So just like timeouts, when you negotiate a connection, you can also keep alive the connections. So it's not a question of I'm doing anything. There's not a timeout. But again, I've had other customers where the keep alive caused problems. Because maybe I've got a very chatty application, but it's only every 2-3 minutes. But it's going to keep the connection open for 60 seconds. Bring that down to 5 seconds, right? And then you'll again see that you're going to get more resources because nothing's free. You need more I/O, you need more memory, like all those things take time and resources. So do things like negotiate a lower keep alive or keep alive timeout as well. And that's both for the backend APIs as well as the clients connecting to the gateway. You negotiated both spots. And the last pattern we're going to talk about today is the decoupled middleware pattern as well as an architecture. So this is a bit of a difference. This is where we use something like a queuing system. Now you're going to say, well, what do you mean by queuing? Well, the reality is sometimes when you're doing web traffic, it's all synchronous. I click something and I get a response. If my backend gets to be slower, everything gets to be slower. The case here is that I go very quickly back and forth with the client, with the gateway. Request comes in, gateway goes and puts it in a queue. Now, the thing is, this is and can be a major architecture change. So usually you want to bring this in earlier. All the other patterns I talked about, you can incorporate usually today without any major impacts to your environments. This one here requires usually a rethink, especially in this end, on the client side, because how does it know when it needs to look at it, right? So we've worked with customers where this provided a 10x increase in availability and performance because the backend systems went at its own rate through a queue, and when it was finished doing its work, puts it back on a second queue. Gateway puts it into its own system in a cache, and then this system makes a query. Now, the front-end client, for example, in this case, one of the examples I'm working with, it would make a call every 5 to 10 seconds. Are you ready? And sometimes we'd say, wait another 15 seconds or 20 seconds, and we'd increase that. But these are very quick 10 millisecond calls, whereas in the past, these were taking up to 60 seconds. And see how the resource is. So this is a very strong architecture pattern, but it requires a bit of work and a bit of knowledge to help work with this. So, and again, the API gateways can definitely help with this. So to summarize, we talked about resiliency really is about stability. And we talked about 6 different patterns where API gateways can help make your APIs more resilient today by covering these 6 different patterns as well. Well, this is also an architecture as well. The timeout, which is all about stop waiting, just short, a lot faster. Circuit breaker, where we reroute during some kind of failure. Bulkhead, it's all about damage containment. Fail fast, where we decide to stop processing, right? We know it's not going to work. Handshaking in terms of health check and negotiations, right? Just make sure we know the systems aren't available. Or maybe put things like keep alive or some kind of negotiations or rate limits in terms of number of requests for that particular connection. And then the decoupled middleware, where you're really putting from synchronous front end to an asynchronous back end. And with that, that's my short, quick overview.